Imagine the vastness of the universe stretching infinitely in every direction, an expanse so immense that even light takes billions of years to traverse from one region to another. Stars shimmer like distant beacons, galaxies swirl in silent ballets, and clouds of gas and dust drift through the cosmic web, unseen by all but the most powerful telescopes. In this grand cosmic tapestry, there exists one of the most mysterious and extreme objects known to science, the black hole. Contrary to the name, a black hole is not a void or an empty pit. It is a region of space where gravity is so intense that nothing, not even light, can escape its pull. This is gravity at its most powerful, a place where the known laws of physics bend and twist under unimaginable forces. To truly understand black holes, we must first grasp gravity itself. Gravity is the force that governs all motion in the universe. It keeps our feet firmly planted on the Earth, guides the moon in its orbit around our planet, and holds the planets in their paths around the sun. Even across the vast distances between stars and galaxies, gravity reaches out, tugging on matter and shaping the large-scale structure of the cosmos. But gravity behaves differently when mass is confined to a very small region. In such extreme conditions, gravity does more than pull, it warps space and time itself, bending the fabric of the universe in ways that defy ordinary intuition. Black holes are the ultimate expression of this warping, where gravity's influence becomes so strong that the very nature of space and time is altered. The story of black holes begins with stars, the titanic engines that light up the night sky. Stars are born in nurseries of gas and dust called nebulae. Within these clouds, gravity pulls matter toward denser regions, creating clumps of gas that grow heavier and hotter as they attract more material. Eventually, the core of one of these clumps reaches a critical temperature and pressure, triggering nuclear fusion. At this point, a star is born. Nuclear fusion ignites like a furnace, converting hydrogen into helium and releasing vast quantities of energy in the process. This energy creates an outward pressure that counterbalances the inward pull of gravity, allowing the star to shine steadily. A star's life is a delicate balance between gravity pulling inward and energy pushing outward. This balance can last for millions, billions, or even trillions of years, depending on the mass of the star. Smaller stars, like our Sun, burn their fuel relatively slowly and live for billions of years, providing stable light and warmth. Larger stars burn hotter and faster, their intense energy output hastening their evolution toward collapse. Eventually, every star runs out of the simple fuel that powers its core. Hydrogen gives way to heavier elements as nuclear fusion progresses through a succession of reactions, forging helium, carbon, oxygen, and in the most massive stars, iron. Once iron accumulates, fusion no longer produces net energy, and the outward pressure that held the star aloft begins to fail. Stars with core masses similar to the Sun, this failure results in a gentle fading. The outer layers drift away into space to form a glowing shell of gas known as a planetary nebula, while the remnant core settles into a white dwarf, a dense, Earth-sized object supported by the quantum pressure of electrons. But stars with initial masses more than about 20 times that of the Sun follow a much more dramatic path. As the core collapses under its own gravity, it can no longer support itself. The result is a catastrophic implosion that triggers a spectacular explosion known as a supernova. In a supernova, the outer layers of the star are blasted outward at tremendous speeds, enriching the surrounding space with heavy elements forged in the heart of the star. Supernovae are among the most energetic events in the universe, briefly outshining entire galaxies as they unleash energy equivalent to billions of suns. The fate of the star's core after a supernova depends on its mass. If the core is below a certain threshold, it may become a neutron star, an incredibly dense object composed almost entirely of neutrons, where a teaspoon of matter would weigh billions of tons. But if the core's mass exceeds this threshold, known as the Tolman-Oppenheimer-Volkoff limit, not even neutron degeneracy pressure can halt collapse. The core continues to compress until it forms a black hole, a region where gravity has overwhelmed all other forces. Here, matter is compressed into an infinitely small and dense point we call a singularity, and the surrounding space is irrevocably altered. At the heart of every black hole lies this singularity, an extreme where our current understanding of physics breaks down. Surrounding it is the event horizon, a spherical boundary with a defining property. Once an object crosses this threshold, escape becomes impossible. The escape velocity, the speed needed to break free, exceeds the speed of light, and since nothing can travel faster than light, nothing can leave. For this reason, black holes do not emit light in any traditional sense, making them invisible against the darkness of space. Instead, we detect them by observing the effects of their immense gravity on nearby stars and gas clouds, on the swirling matter in accretion disks, and on the fabric of space itself. The radius of the event horizon, known as the Schwarzschild radius, is directly related to the mass of the black hole. A black hole with a mass equal to that of our Sun would have a Schwarzschild radius of about 3 kilometers. This means that all the Sun's mass would need to be compressed into a sphere no larger than a small city in order to become a black hole. Supermassive black holes, on the other hand, can have radii measured in millions or billions of kilometers, enveloping regions far larger than our entire solar system. These supermassive giants reside at the centers of galaxies, exerting immense influence on their surroundings and shaping the motion of stars and gas on cosmic scales. In our own Milky Way galaxy, astronomers have identified a supermassive black hole known as Sagittarius A*, with a mass about 4 million times that of the Sun. Although it is invisible in optical light, its presence is revealed by the rapid orbits of stars in its vicinity and by high-energy emissions from matter swirling toward it. The discovery and study of Sagittarius A have provided profound insights into the role supermassive black holes play in galaxy formation and evolution. Yet many questions remain unanswered. How did such enormous objects form so early in the history of the universe? What processes govern their growth? These mysteries continue to challenge scientists and drive new observations. One of the most luminous features associated with black holes is the accretion disk, a swirling, flattened ring of matter that forms as gas and dust spiral inward. As this material falls deeper into the gravitational well of the black hole, friction and gravitational forces heat it to extreme temperatures, causing it to emit radiation across the electromagnetic spectrum. In some active galactic nuclei, the brightness of the accretion disk can overwhelm the combined light of all the stars in the host galaxy. Paradoxically, it is not the black hole itself, but the matter around it that shines so brilliantly, allowing astronomers to infer the presence of these otherwise invisible objects. Black holes can also produce powerful jets of particles and energy. In some systems, magnetic fields near the accretion disk can accelerate particles to near-light speeds, ejecting narrow beams of matter far into space. These jets can extend for thousands of light years, impacting interstellar gas and influencing star formation in distant regions. The interplay of gravity, magnetism, and high-energy physics in these environments creates some of the most dynamic and energetic phenomena in the universe. To understand black holes, we must also understand the deeper nature of space and time. Einstein's theory of general relativity describes gravity not as a force, but as the curvature of space and time caused by mass and energy. Near a massive object like a black hole, this curvature becomes extreme. Time itself slows down relative to distant observers, a consequence known as gravitational time dilation. If an astronaut were to fall toward a black hole, an outside observer would see their descent slow and freeze as they approached the event horizon. Yet from the astronaut's own perspective, they would cross the threshold without noticing any abrupt change in the flow of time. This duality of experience highlights the profound and counterintuitive nature of spacetime near black holes. Imagine traveling closer to a black hole. Gravity becomes stronger with each passing moment, stretching not only space, but also physical objects. This process, known as spaghettification, occurs because gravity's pull is stronger on the side of an object closer to the black hole than on the far side. The difference in gravitational force can stretch even the sturdiest objects into elongated forms, resembling long strands. For smaller black holes, these tidal forces become extreme well before the event horizon is reached. For supermassive black holes, the tidal gradient near the horizon may be gentler, allowing one to pass inside before experiencing severe stretching. Regardless, all paths inside the event horizon ultimately lead inward toward the singularity, where space and time become so entangled that conventional physics ceases to apply. In 1974, physicist Stephen Hawking made a revolutionary prediction: black holes are not truly black. By combining principles of quantum mechanics with general relativity, Hawking showed that particle-antiparticle pairs forming near the event horizon could result in one particle escaping while the other falls in. This effect causes black holes to emit a faint glow of radiation, now known as Hawking radiation. Although this radiation is incredibly weak for astrophysical black holes and far beyond current observational capabilities, its existence suggests that black holes can lose energy and mass over time. Over unimaginably long timescales, even the largest black holes could evaporate entirely, leaving behind only radiation and information imprinted on the surrounding spacetime. This possibility raises a profound question in physics: what happens to the information about everything a black hole has consumed? According to quantum theory, information cannot be destroyed. Yet if a black hole eventually evaporates, what becomes of the data carried by all the matter that fell into it? This conundrum is known as the black hole information paradox, and it sits at the heart of efforts to reconcile general relativity with quantum mechanics. Some theoretical models suggest that information may be encoded on the event horizon itself, preserved in subtle correlations within Hawking radiation. Others invoke the holographic principle, proposing that the entire three-dimensional state of matter falling into a black hole may be represented on a two-dimensional surface. These ideas hint at a deeper and more unified description of reality, one that transcends our current understanding of space and time. Observing black holes directly poses immense challenges because they emit no light of their own. Instead, astronomers rely on indirect evidence. One method involves tracking the motions of stars and gas near the suspected location of a black hole. If stars orbit at high speeds around an unseen mass, this indicates the presence of an extremely compact object exerting tremendous gravity. Another method focuses on emissions from accretion disks and jets, which can shine brightly in X-rays and other wavelengths detectable by space telescopes. Gravitational waves, ripples in spacetime caused by accelerating masses, offer yet another window into black hole dynamics. When two black holes merge, they release a burst of these waves, carrying information about their masses, spins, and the nature of gravity itself. The first direct image of a black hole was captured in 2019 by the Event Horizon Telescope, an international collaboration linking radio observatories around the globe. The image revealed a glowing ring of light surrounding a dark central shadow, the silhouette of the black hole's event horizon in the galaxy M87. This landmark achievement confirmed long-standing predictions of general relativity and opened a new era of observational black hole science. In 2022, the Event Horizon Telescope succeeded once again, imaging Sagittarius A, the supermassive black hole at the center of our Milky Way. These images provide unprecedented insights into the behavior of matter and energy in the extreme gravity near black holes. Black holes are not merely theoretical constructs, they are observable phenomena that shape galaxies, emit tremendous energy, and influence the universe on grand scales. While we cannot see a black hole directly, we can observe its effects on the surrounding environment. Stars orbiting an unseen mass, glowing accretion disks, and high-energy jets all provide evidence of these cosmic giants. Observations across the electromagnetic spectrum, from radio waves to X-rays, reveal the presence and behavior of black holes in remarkable detail. The center of the Milky Way resides Sagittarius A*, a supermassive black hole weighing about 4 million times the mass of our Sun. Its presence is inferred from the rapid orbits of stars near the galactic center, moving at thousands of kilometers per second under its intense gravitational pull. Observations with advanced instruments, such as adaptive optics and radio interferometry, allow scientists to track these stellar motions precisely, confirming the black hole's mass and location. The galaxy M87 hosts another supermassive black hole, famously imaged by the Event Horizon Telescope in 2019. The glowing ring surrounding its dark center represents hot plasma orbiting the event horizon, providing a striking visual confirmation of theoretical predictions. This image not only captures the silhouette of the black hole, but also allows scientists to measure its size, rotation, and the behavior of matter under extreme gravity. Such observations mark a new era in black hole astronomy. Supermassive black holes influence the evolution of galaxies. Their gravitational pull helps anchor stars, while their jets and radiation can regulate star formation. Active galactic nuclei, powered by black holes consuming matter, can inject energy into surrounding gas clouds, preventing runaway star formation and shaping the growth of galaxies over billions of years. Understanding the relationship between black holes and galaxies is essential for comprehending the structure and history of the universe. Binary black hole systems provide additional insights. In these systems, two black holes orbit each other, gradually spiraling inward due to the emission of gravitational waves. When they merge, the collision releases tremendous energy, sending ripples through spacetime detectable across the cosmos. The first detection of gravitational waves by the LIGO Observatory in 2015 confirmed these predictions, opening a new window into the universe. These observations allow scientists to study black hole masses, spins, and dynamics in ways never before possible. Gravitational waves offer a complementary perspective to traditional electromagnetic observations. Unlike light, which can be absorbed or scattered, gravitational waves propagate freely through the universe, carrying information about cataclysmic events. By analyzing these waves, astronomers can reconstruct black hole mergers billions of light years away, exploring populations of black holes in the early universe. The study of gravitational waves is rapidly transforming our understanding of cosmic evolution. Supermassive black holes are not uniform. They vary in mass, spin, and activity. Some are dormant, quietly influencing their surroundings without emitting much radiation. Others, called quasars, shine with extraordinary luminosity as they consume vast amounts of matter. Quasars can outshine entire galaxies, their brightness visible across billions of light years. These extreme objects provide a glimpse into the early universe, revealing how supermassive black holes formed and grew during the first billion years after the Big Bang. Observations suggest that nearly every massive galaxy hosts a supermassive black hole at its center. The co-evolution of galaxies and black holes is a central question in astrophysics. How do black holes grow so quickly? How do they regulate star formation? How do their jets and radiation influence galactic environments? These questions drive research using space telescopes, radio arrays, and high-energy observatories, connecting black holes to the broader cosmic ecosystem. Black holes also have a profound role in shaping cosmic structure. Their mergers can redistribute energy across galactic cores, influencing stellar orbits and gas dynamics. Jets from active black holes can clear out interstellar gas, suppressing or triggering star formation. Through these mechanisms, black holes contribute to the formation of galaxy clusters, the large-scale filaments of the cosmic web, and the overall evolution of the universe. Their impact is both local and cosmic, subtle yet transformative. The study of black hole mergers has revealed remarkable phenomena. When two spinning black holes collide, they can produce recall velocities that send the newly formed black hole hurtling through space. These mergers also produce gravitational wave signals that encode information about the spin alignment, mass ratio, and orbital dynamics of the progenitor black holes. By analyzing these signals, scientists can probe the conditions of black hole formation and the history of stellar populations across cosmic time. Black holes are also key to understanding the ultimate fate of matter and energy in the universe. Over immense timescales, black holes may dominate the final stages of cosmic evolution. Stars will burn out, galaxies may collide, and black holes will consume remaining matter. The universe may eventually enter a state dominated by cold, dark remnants, with supermassive black holes persisting as the last significant structures. Hawking radiation suggests that even these black holes will slowly evaporate over inconceivably long timescales, releasing energy and information back into the cosmos. Despite their extreme nature, black holes are central to our understanding of fundamental physics. They test general relativity in strong gravitational fields, explore the limits of quantum mechanics, and challenge our understanding of information conservation. Every observation, from the orbit of a star near Sagittarius A to the detection of gravitational waves from merging black holes, reinforces our understanding of how the universe operates under extreme conditions. The philosophical implications of black holes are equally profound. They confront us with the limits of knowledge, the inevitability of singularities, and the nature of space and time itself. They raise questions about determinism, the flow of time, and the ultimate fate of information. In contemplating black holes, humanity engages with both the observable universe and the boundaries of imagination, exploring concepts that transcend everyday experience. Through simulations, astronomers model the complex physics near black holes. Computational methods allow scientists to recreate accretion disks, jets, and mergers in virtual environments, testing theoretical predictions against observational data. These simulations reveal the intricate interplay of gravity, magnetism, and radiation, providing insights into phenomena that cannot be directly measured. They serve as laboratories where extreme physics can be explored safely and with precision. Black holes also provide insights into the early universe. Observing quasars billions of light years away allows scientists to probe conditions shortly after the Big Bang. These distant supermassive black holes challenge existing models of growth and formation, suggesting that black holes can accumulate mass extraordinarily rapidly. Understanding these processes informs our knowledge of galaxy evolution, cosmic structure formation, and the timeline of the universe. Recent discoveries continue to push the boundaries of black hole science. Intermediate mass black holes, with masses between stellar and supermassive black holes, have been identified, filling gaps in our understanding of black hole populations. Their formation and prevalence provide clues about the evolution of stellar clusters, galaxy mergers, and the mechanisms that drive mass accumulation in black holes. Each new detection adds another piece to the cosmic puzzle. The interplay of observation, theory, and simulation reveals a universe profoundly shaped by black holes. They act as engines, regulators, and markers of cosmic evolution. Their influence extends from individual stars to entire galaxies, affecting matter, energy, and the flow of time. By studying black holes, scientists uncover not only the nature of these exotic objects, but also the broader mechanisms that govern the cosmos. Looking to the future, black hole research will continue to expand with next-generation telescopes, space observatories, and gravitational wave detectors. Instruments like the James Webb Space Telescope, the Laser Interferometer Space Antenna, LISA, and the extremely large telescope promise unprecedented resolution, sensitivity, and reach. These tools will allow scientists to observe black holes in new wavelengths, detect more mergers, and study the interplay between black holes and their host galaxies in greater detail than ever before. Black holes are also central to the search for a unified theory of physics. By studying their interiors, singularities, and horizons, physicists hope to reconcile general relativity with quantum mechanics. Concepts like the holographic principle, quantum entanglement across horizons, and the behavior of information near singularities may provide the keys to understanding gravity at the quantum level. Black holes, therefore, are not just cosmic objects, but gateways to fundamental knowledge about the universe. As we observe, theorize, and simulate black holes, we are reminded of their dual nature: destructive yet enlightening, invisible yet influential, extreme yet essential. They represent the frontier of human understanding, pushing science to its limits while inspiring imagination and curiosity. In contemplating black holes, we confront both the grandeur and the mystery of the universe, learning not only about these extraordinary objects, but also about the fundamental laws that govern all existence. In conclusion, black holes are among the most remarkable phenomena in the universe. From stellar remnants to supermassive giants, they shape galaxies, emit immense energy, warp space and time, and challenge the boundaries of physics. Observations of black holes, including M87 asterisk, Sagittarius A, and countless mergers, continue to reveal new insights into the cosmos. Gravitational waves, accretion disks, jets, and the evaporation of black holes all demonstrate the profound influence these objects have on matter, energy, and time. Through the study of black holes, we gain a deeper understanding of the universe's structure, evolution, and ultimate fate. We confront questions about the origin of galaxies, the distribution of mass and energy, the nature of time, and the conservation of information. Black holes serve as cosmic laboratories, testing theories of gravity, quantum mechanics, and high-energy physics under the most extreme conditions imaginable. Black holes also inspire philosophical reflection. They challenge our perception of reality, the limits of knowledge, and the nature of existence itself. As objects that trap matter, energy, and information, yet reveal their influence across cosmic distances, they invite contemplation about the interplay between the seen and unseen, the known and unknown, the finite and infinite. Finally, black holes remind us of the profound beauty and complexity of the cosmos. They are not merely points of destruction, but essential actors in the story of the universe. By studying them, humanity explores the extremes of nature, tests the limits of understanding, and glimpses the extraordinary possibilities that lie beyond our everyday experience. Black holes are at once mysterious, illuminating, and essential, symbols of the universe's vastness and the endless pursuit of knowledge. Black holes do not exist in isolation. Many are part of binary systems, where a star orbits a black hole. In these systems, the black hole's gravity can strip matter from its companion, forming an accretion disk and triggering bursts of high-energy radiation. These systems offer rich laboratories for studying gravity, matter under extreme conditions, and the processes that drive high-energy astrophysics. By observing these dynamics across different wavelengths, from radio to X-ray, astronomers can piece together a multifaceted picture of how black holes influence their environments. As our understanding deepens, so do the questions. How did supermassive black holes grow so large so early in the universe's history, just a few 100 million years after the Big Bang? Do primordial black holes, formed in the earliest instance of cosmic history, still exist, and could they account for some portion of dark matter? What lies beyond the event horizon, in a realm where spacetime and quantum mechanics collide? These questions drive new theories, new observations, and new instruments designed to probe the frontier of knowledge. Black holes are not merely astrophysical curiosities, they are profound gateways to understanding the fundamental nature of reality. In every sense, they push science to its limits. They test general relativity under conditions of extreme gravity, challenge quantum mechanics to account for information preservation, and invite us to rethink the fabric of space and time. Yet in their darkness, they illuminate our understanding of the cosmos and reveal the extraordinary richness of the universe. To truly understand black holes, one must venture beyond the mere surface, beyond the event horizon, and explore the physics that govern these enigmatic objects. The black hole is more than a region of intense gravity. It is a laboratory where the universe tests the limits of space, time, and matter. Inside, the familiar rules of physics, those that govern our daily experience, begin to break down. Space and time intertwine, matter behaves in ways that defy intuition, and energy reaches extremes that challenge our understanding of reality. The singularity lies at the core, a point of infinite density where all the mass of the black hole is compressed into an infinitely small volume. Here, general relativity predicts that spacetime curvature becomes infinite. The known laws of physics, both classical and quantum, cease to provide a reliable description of reality. Some physicists speculate that a theory of quantum gravity, not yet fully developed, may resolve the singularity into a more comprehensible structure. Until such a theory is found, the singularity remains one of the greatest mysteries in all of physics. Surrounding the singularity is the event horizon, the boundary beyond which no information can escape. To an outside observer, it is as if anything that falls into the black hole disappears, leaving no trace. However, the perspective of someone falling in is radically different. From their point of view, they continue to move normally, passing through the horizon without perceiving an abrupt boundary. This duality of perception lies at the heart of our understanding of black holes and the complex relationship between gravity, time, and space. Inside the black hole, spacetime is warped to extreme degrees. Time behaves differently depending on the observer's position relative to the event horizon. Gravitational time dilation causes clocks near the horizon to run much slower compared to distant observers. This means that while someone far away may watch an object fall into a black hole seemingly frozen in time, the object itself experiences time flowing normally. This bizarre effect is a direct consequence of Einstein's theory of general relativity and illustrates how profoundly black holes distort the fabric of the universe. As an object approaches the singularity, tidal forces become overwhelming. Gravity at one end of an object is stronger than at the other, stretching it into a thin, elongated shape in a process famously called spaghettification. This extreme stretching is not just a metaphor, it is a literal transformation caused by the differential gravitational forces. Small black holes produce this effect very far from the singularity, while supermassive black holes, with their much larger radii, allow an object to cross the event horizon before tidal forces become lethal. Regardless of size, the ultimate fate inside a black hole is inescapable. All paths lead toward the singularity. Even outside the event horizon, black holes produce fascinating and violent phenomena. Accretion disks, composed of gas and dust spiraling into the black hole, heat to millions of degrees due to friction and gravitational compression. These disks emit high-energy radiation, including X-rays, which can be detected by space observatories. In some systems, this radiation is so powerful that the black hole becomes one of the brightest objects in the universe, illuminating regions far beyond the reach of ordinary stars. Some black holes also generate colossal jets of matter and energy, ejected at nearly the speed of light along the rotational axis. These jets, powered by magnetic fields and the rotational energy of the black hole, extend for thousands of light years, shaping the evolution of galaxies and influencing star formation in surrounding regions. The study of these jets provides crucial insights into how black holes interact with their environment and how they influence cosmic structure on massive scales. Stephen Hawking's revolutionary work introduced a surprising twist to the story. According to his theory, black holes are not completely black. Quantum fluctuations near the event horizon allow particle-antiparticle pairs to form, with one falling into the black hole while the other escapes. This process creates a faint radiation known as Hawking radiation. Over immense timescales, this radiation can cause black holes to lose mass and eventually evaporate entirely. The concept that black holes are not eternal challenges long-held assumptions and bridges the realms of quantum mechanics and general relativity. Hawking radiation raises profound questions about information. According to the principles of quantum mechanics, information about matter cannot be destroyed. If black holes evaporate, what becomes of the information contained within the matter they consumed? This paradox, known as the black hole information paradox, challenges our understanding of physics at the most fundamental level. Some theories suggest that information is preserved on the event horizon in a holographic form, while others propose that subtle correlations in Hawking radiation carry this information outward, ensuring that nothing is truly lost. Wormholes, a theoretical consequence of Einstein's equations, present an even more exotic possibility. Often depicted in science fiction as shortcuts through spacetime, wormholes are hypothetical tunnels connecting distant points in the universe. While their existence remains speculative, solutions to the equations of general relativity suggest that they could, in principle, exist. A black hole might form one end of a wormhole, with an exotic form of matter holding it open. Whether any traveler could survive passage through such a structure is unknown, but the mathematics of wormholes provides a tantalizing glimpse into the possibilities of warped spacetime. Falling into a black hole challenges every assumption about the universe. Near the event horizon, light is redshifted to longer wavelengths, becoming invisible to the human eye. The very geometry of space bends, causing distant stars to appear stretched and distorted. As one descends, the familiar three dimensions of space begin to merge with the flow of time, and the distinction between past, present, and future blurs. This extreme warping provides scientists with an unparalleled laboratory to test theories of gravity, quantum mechanics, and the nature of spacetime itself. Inside rotating black holes, known as Kea black holes, the structure becomes even more complex. These black holes spin at incredible rates, dragging spacetime along with them in a process called frame dragging. The singularity in a Kea black hole is not a point but a ring, and in theory, it could permit passage to other regions of spacetime. Whether such a passage could exist in reality, or whether it is purely a mathematical curiosity, remains a topic of active research and speculation. The inner regions of black holes are governed by extreme physics. Pressure, density, and gravitational forces reach magnitudes that cannot be recreated on Earth. Matter behaves in ways that challenge classical intuition, quantum effects become significant, and energy densities approach infinity. These conditions test the limits of both relativity and quantum theory, highlighting the need for a unified theory of quantum gravity to fully understand the singularity and its surroundings. Black holes also influence the very structure of the universe through gravitational waves. When two black holes spiral into one another and merge, they send ripples through spacetime, detectable as faint distortions that travel across the cosmos. The first detection of gravitational waves in 2015 confirmed these predictions, opening a new era of astrophysics. These waves allow us to observe phenomena invisible to traditional telescopes, providing information about black hole masses, spins, and the dynamics of their collisions. Inside a black hole, energy and matter interact in extreme ways. Tidal forces stretch and compress objects, while gravitational time dilation alters the perception of time. Quantum processes near the horizon introduce radiation, and singularity physics suggests an ultimate breakdown of conventional reality. These interactions provide clues about the unification of physics, pointing toward a future theory that could reconcile general relativity with quantum mechanics. Studying black holes is not just about observing distant objects. It is about testing the very foundations of physics. They reveal the limits of our understanding and push scientists to explore extreme conditions that cannot be reproduced in laboratories. Every observation, every simulation, and every theoretical insight brings us closer to understanding the profound mysteries of the cosmos. Despite their dangers and extremes, black holes are natural cosmic laboratories. They allow us to study fundamental physics, from spacetime curvature to quantum phenomena, under conditions that are impossible to replicate elsewhere. They are both destructive and enlightening, consuming matter while revealing the deepest truths about the universe. Black holes continue to inspire both awe and scientific inquiry. From the dramatic deaths of massive stars to the slow evaporation predicted by Hawking radiation, from the theoretical tunnels of wormholes to the warping of spacetime, these objects challenge our perception of reality. They are simultaneously destructive, illuminating, and essential to understanding the cosmos at the most fundamental level. Every black hole is a testament to the extreme power of gravity and the mysterious interplay between matter, energy, and spacetime. As scientists study them, they uncover new layers of complexity, from accretion disk physics to jet formation, from time dilation effects to the information paradox. Each discovery illuminates not just the nature of black holes, but also the underlying principles that govern the universe itself. While the singularity remains hidden, inaccessible, and beyond direct observation, its existence drives theoretical exploration. Models of black holes inspire new ideas about the quantum nature of gravity, the holographic principle, and the ultimate fate of matter and energy in the universe. They push physicists to confront questions about the very fabric of reality and the limits of scientific knowledge. Black holes are more than astronomical objects. They are profound tests of theory and imagination. They challenge us to reconcile the cosmic and the quantum, the infinitely large and the infinitesimally small. By studying them, humanity seeks to glimpse the underlying order of the universe, to understand how space and time operate under the most extreme conditions, and to explore the boundaries of the known and the unknown.